Hi, welcome back again to the static review session. In this session, we'll work about equilibrium of a body. Um, get ready. This is finding support reactions for 2D and 3D. Please also review before starting if you haven't looked to the session before that, number 4, free body diagrams. Review it before going into this session. So get ready, paper and pen, and try to follow. You can stop it as many times you want, but this is one of the important steps in finding support reactions. So in the previous session, we learned how to draw the free body diagram for a coplanar non-concurrent force system. And this means that coplanar is a 2D, and non-concurrent means that they don't meet in one point. All forces don't meet in one point. In a previous session, we spoke about first drawing a free body diagram and then draw the support reactions. This is what we will try to find today, now in this session. Always think at a support what it will prevent from, and then you just place the reactions. This is known as a pin support. Pin support will allow rotation, but it won't allow motion or movement. So you look at the y direction, it won't allow it to move. So you place reaction, and in the x, you place a reaction in the x. A roller support will not allow motion in the vertical, but it will allow motion in the horizontal. So we don't place support, and it won't allow rotation. We don't place also moment support. Um, in real world, if you look at if you're interested in bridges, look under the bridge and see the support. A roller support in a bridge is like a cylinder and two plates on top of each other, on the top and the bottom, and you have it like a steel cylinder. It is placed to allow motion. This is very important to allow expansion, contraction, and any motion that could happen to structures. Um, so, following step, how to find these support reactions. In equilibrium of a body, um, we say equilibrium because this system actually not moving anywhere. So it is in equilibrium, which means that if we get sum of all forces and moments should equal 0. We use this equation of equilibrium 3 in a case of coplanar non-concurrent, then we have 3 equations of equilibrium. Sum of the forces parallel to the x-axis should equal 0. Forces parallel to the y equals 0. Force and moments about the point A should equal 0. Or about any point in the system should equal 0. We pick the point A. We come back to the moment shortly. But let's start by placing or writing the equations. Now, for some of the forces parallel to the x-axis, we just add all forces that are parallel to the x-axis. We pick that this direction going in the positive is the positive direction, or going to the right is the positive direction of the equations. So followed by that, just write the equation of equilibrium. Here, if you look at all forces, the only forces that are parallel to the x-axis is the x component of that 95 kilonewton and the ax. Ex is moving towards the negative side of the x-axis. And the x component is using, because the x component is adjacent to the angle, then we use the cosine the angle. So this is the x, so we can simply just solve it for x, and you get the first reaction, support reactions. Ex is 63.57 kilonewton. It is positive, which means that this assumption that we first gave, that the air would be in this direction, is correct. If you would have got a negative sign here, then it means you have to change it to the other direction. Followed writing the equations of equilibrium for the y-axis. Before that, we see here a distributed load. Distributed load can simply divide it into major shapes, rectangles, and triangles. And then trying to find a resultant which simply is just the area of. So if I divide this into this rectangle that has a height of 15 and base of 6, and I call this F1, which is a resultant of this distributed load, and then F2 is the resultant of this distributed load, which is the height in that case is the 45 minus 15, the 30, and the base is 6. So let's write the equation of equilibrium. You have vertical forces in the y directions. You have the bx, the by, the ay, these two forces, the vertical component of that. I don't need to worry about the moment, it's a moment. And then you have the F1 and F2. So if we start writing, taking the positive y direction as a positive, so we start here negative 120. Then the vertical component of the 95, which using sine the angle because it's the opposite to the angle. And then taking this F1 is simply finding the resultant of that distributed load or finding the area of that distributed load. So it's height 15 times base 6. That's the resultant. Acting downwards, so it's negative. And then also finding the resultant of that triangle is the area of that triangle. So you have the 30 is the height, which is the 45 minus 15 because we're taking just this triangle, and then multiply it by the base, the 6, and then half of that for the area of the triangle. This is, and it's acting toward downwards, so which is negative. And then you have the ay and the by that are positive. Now this equation cannot be solved because you have two unknowns. And that's why we could have started with the moment equations right away. But I left it to the end to talk a little bit about the moment. Moment of a force is a force times a perpendicular distance between a point of rotation and the force line of action. So if we take the moment about this point A, equation of equilibrium says if you take a moment about any point in the system, and because it's in equilibrium means that it's not moving or rotating, then it should equal 0. We picked point A to get rid of one of the unknowns. First, I get rid of the ax because it's just passing or cutting through the point, and ay cutting through the point, so that we'll have only this one unknown in that case. So let's write the equations for the moment and go with that one by one. So first I will pick the positive rotation, which is the counterclockwise, to be the positive. So if I get the by moments, then you have the force multiplied by the perpendicular distance, which known also as the moment arm, connected between the point of rotation, so I'm taking a moment about this point, and cutting through the line of action of the force. So that perpendicular distance was nothing to be but adding these three numbers. 3 plus 4, 7 plus 5 is 12. The following is taking this force. So you have that force is rotating clockwise. Remember that we choose counterclockwise to be negative, to be positive. Then you have this is a negative. The force is 120 multiplied by that perpendicular distance is 3. And then again the force perpendicular to that line, which is the vertical component of that 95. Now it is also rotating about this point in clockwise. Remember again, counterclockwise is positive, that's why we use a negative. And then multiply by the distance or the moment arm or the perpendicular distance. And so let's stop here a little bit. If you would take the negative component is actually passing through the point of the horizontal component is passing through the point of rotation. So it's line of action. That's why moment. There's no moment arm. Uh, uh, and in that case, we don't take the horizontal component. So it's only the vertical component that is taken. Another way, if we look at what is the perpendicular distance from this point to the line of action, it would be difficult to calculate. That's why we work with the components. So the following is taking this 35. So the 35 is already a moment. So it's a kilonewton meter. It is already a moment, or we call it also a couple moment. So the 35 rotating clockwise, counterclockwise, which is positive as we choose, then it's positive. And then we come to these two forces, F1 and F2. F1 we said is 15 times 6, like here. It's rotating in the clockwise, so it is negative. 15 times 6, that's the force itself, and then times the moment arm, which is the distance from that point of rotation to the force line of action. This force acts exactly at the centroid of the rectangular shape. So the centroid, if it's a rectangular, then it's exactly in the middle. Then you have acting at 3 and 3, so you have 3 plus 5 plus 4 plus 3, and this is where you come to that 15. So it's 15 times 6, the force F1, times 15 moment arm, and negative is the rotation. And then finally, the last force, which is this distance, that triangle. So again, the force resultant, 30 times 6 half, that's the area of the triangle, rotating clockwise, negative, and then multiplied by the moment arm. That force is acting exactly at the centroid of this triangle, which is 1/3 and 2/3. So because I'm taking a moment at this point, so I have to add 3 plus 4 plus 5 plus 1/3 of the 6, which is 2, and this is where you come to the 14. Please review carefully. If I would write that, then I would go back again and review it. Um, Review every single term or member of a term that you look at. So if you look at this, for example, you have negative represent the rotation, a force, its component, vertical component, and the moment arm. Don't miss any of these members in that term or in any other term. Here, 15 times, 30 times 6 half, that's a resultant of the triangle, multiplied by 14. First, the 1/3 adding to the distance depends on you where you take your moment amount. And of course here, the sign is the important. Any mistake you do there gets you all answer are wrong. So followed by that, you solve it for By. You get that's the value of By in kilonewton, and then substitute here, you get the Ay. And this is coplanar non-concurrent force system. Now let's move to the interesting part. Non-coplanar, 3D, non-concurrent, they don't meet in points, in the same point, force system. In a previous session, session 4, we talked about how to find the support reaction, so please review that for this same problem. But just as a quick review, always place reactions wherever you see there's no this prevention of motion or rotation is in this that this support will cause. So in 3D, important is that you have to write the equation of equilibrium. How many are those? 2, 3, 4. No, there are 6 equations of equilibrium because we are in 3D. Also, notice that number of unknowns has to be equal to the number of equations of equilibrium. If it's not, which we call it a statically indeterminate system, you will learn how to build another equations that will help, but this is in mechanics materials. But because statics, we work only with equilibrium of equation of equilibrium, then number of unknown has to be equal to the number of equations. So I would right away start with the equation. So forces in the x, list all forces in the x direction. So you have ax, bx, and this 88. I took in that case that this direction, which is I just picked it to be in a positive direction, right? So you have that direction is positive, ax and bx, and then negative 88, and then continue with the y direction. So list all the forces and reactions that are parallel, including like cy and ay. So I have ay and cy. So I pick this direction to be the positive, and and then you have minus 153, and then the positive component, this horizontal component of the 300 pounds using the cosine, and then listing the all the z going the upwards is a positive, so BZ, CZ, and then negative 177, and then the vertical component. So this way we finish the first three. Now, if you were able to solve any, like if you didn't have the BX, for example, we're able to solve it and substitute. But in that case here, I have already a 6 unknowns, but 3 equations. Then I have to write the 3 other equations. So we continue. Now here comes interesting. Moments. Some of the moments about the X. I give you an interesting tip. Um, if you cannot just see what rotates about the x-axis from a 3D image, I advise you to draw a 2D image of the other two. I'm taking the moments about the x, so I draw these two positive direction of the z and a y axis, and the x is coming just out of the plane, so it's coming out. And then I start drawing. If you look at here, so I'm looking in this direction. So I would draw first this line, which represent that line, and then from at the end of it, then I draw a vertical line to represent this part, and I added these dimensions. Notice that this part of the pipe that goes B from that point to C, it's just behind and parallel to that X, so it's just behind this point, so I don't see it. The following step, drawing all the forces that rotate about the x-axis. So, for example, these three forces are not rotating about the x-axis. And why is that? Because they just cut, one of them is just, first it's a parallel and it's just passing through the x-axis, so it's not rotating. These two are cutting through the axis, so they are not rotating. I don't need to worry about these. Let's go from the top there. If you look at this 300 and you're talking about rotating about the x-axis, so obviously you have this 300. Oh, if you go for the so this 300 will rotate about both axes, but if you look at the BZ, which rotate, but BX is parallel, so it's not rotating. You move up and then you go to point A. BX is parallel, but AX is parallel, so it's not rotating, but AY is rotating. And then finally, as I said, that 300 pounds is rotating, both are rotating about the x-axis. So this is actually all what rotates about the x-axis. These two forces, they cutting through the axis, so I don't need to worry about. Now it will makes it much easier to write the equation of equilibrium. But before that, we have to think about the rotation. Usually, if you think about how to write the rotation, use the right hand rule. Your thumb is towards the positive direction of the axis, and then rotate your fingers. Then this is the rotation of the positive. It is actually exactly as if you go here counterclockwise is positive. Just look at it. So I have these three forces to add in the equations. So, and that's the positive direction. So we start with the 300 components. The, the sine, which is the vertical component, multiplied by, so extend the perpendicular from the point of rotation to the line of action of the vertical component. This is 5. And that's the force vertical component rotating counterclockwise positive. And then you have the 300, the horizontal component, extend line of action, and that point perpendicular. So this is the distance. Please don't make mistakes in taking that distance. It happens to be equal, but you have to be careful. So this also times 5, but this is that 5. And then you have AY rotating positive, counterclockwise, and multiply it by that distance. So extend line of action. Please, some would take that 5 wrong. The moment arm is that extend from the point of rotation that cuts through perpendicular through the force line of action, and this becomes that 4. And then negative, because this the BZ is rotating negative, and multiplied by the moment arm is 3. So that's the equation for the X. Now I still need to have moment about the Y-axis. So let's do that too. I draw the axis where the positive two other axes, the plane of the other two axes, and Y coming out of the plane. So I'm looking in that direction now. So if you look there, you see that I can draw this line to the right. And I can back here, I can draw this exactly up. And this line is just behind that. So what else can you draw that rotates about the y-axis? Again, because we're talking about the y-axis, I can eliminate all these forces because they all cut through that line. So they don't rotate. I can get rid also of the AY and the CY because they are parallel. So all I need to take is the CZ and the AZ. The Y component of the 300 is not, and the Z component cut through. So only these two forces actually that rotates about the Y axis. So if I need to write the equations for the Y, I can simply, again, right hand rule, rotating this direction, which means that it's also counterclockwise, positive, and I can write the CZ times the 5 and the AX times the 4, and this is the fifth equation. The last equation about the z-axis is actually much easier than about the x and the y, because you can look from the top, and that's the positive right hand rule, positive rotation. So what do you see? Start with the 300. The 300, the x component cut through, and this is parallel, so the 300 is not rotating about the z-axis. AY is cutting through the axis, not taking, but AX is rotating about the z-axis. So I will take AX. I will take BX because it's rotate, but BZ not. AZ not, but CY. Yes, so I can write this equation. So only the CY times moment arm 5 rotating positive, AX times 5, which is this moment arm. Please, it's not the 4, it's not parallel to the axis, it's perpendicular to it. And BX, and rotating negative, opposite to that right hand rule. And then finally BX also multiplied by the 3 that distance, and rotating opposite. So we have the six equation of equilibrium. How can I solve that? If I just would list them, these are the six equations. You can spend hours and hours to try to solve with a substitution, but your calculator can help you a lot with a matrix function. Please review that for each calculator. You can Google, even if you don't have, if you got your calculator from your brother or sister, and you don't have the guide, just Google the calculator user guide, and you can find it right away. So the following step is just building a matrix. For six equation, the first question it asks you the calculator what kind of matrix. This is 6 by 7 matrix. So I would first list, it's up to you. You can list just to make sure that each column will occupy only this value, the value of this variable. And then, so you have six column, the seventh column is occupied for the constant values. So I go for with each formula. So you have the first formula, you have a value for the first variable is 1, and then you have nothing for AY, you have 1 for BX, nothing, 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 and then that 88.4, please notice that this is the calculator as it programmed, and it has to be on the other side of the equation. That's why we change the sign, then it becomes positive. We list this too. So again, that's the, it is positive, it's moved to the x you have, and then add it together with that. So all the constant will be added together and then move with a changing the sign. And then you have EY and CY. The same thing goes for that. And then here notice for the moment x, so you have all this as the constant will be moved in the other side with a negative sign. AY has a 4 multiplied by it, and BZ multiplied by the negative 3, and then the same goes for the other two equations. So you have this matrix, and please be careful any change. And I would I would invite you to, probably after doing all of that and you go to just correctly change maybe only the sign of that 3, or put this here instead, and see how the answer will be totally different of the values of that. So you have to be careful. That's why it's better to first write it down, write this matrix, and then review again with the equations. Please think about mistakes where you're not allowed to do mistakes, and mistakes can come with a very silly mistakes, like putting or not paying attention at where to put the one, or using here positive instead of that negative would change the whole answer. So we build a matrix, you solve it, check your calculator user guide, and you will get an answer like that in a calculator. One, that's why it's for you to look at that you have occupied the first column for AX. So this right away means that AX is equal negative 632. So negative again means that it has to be in the opposite direction of this assumption. And here AY is 140, right direction. BX is 718. BZ is 894, upwards, correct. CY is negative, which means it has to be in the opposite direction. And CZ is negative, which has to be in the opposite direction. So, final note, please be careful when you build this matrix. Be careful when you write the equation of equilibrium. Any mistakes in the equations, in the sign, in the moment arm, in direction will give you a wrong answer for those. The matrix, as I told you, if you just try to just go back to the matrix and change just one number, just a sign, switching, and see, you will get a total, all the answer will be here wrong, and with a big difference. So This wraps up this interesting uh, session, and see you next session. Thank you.